The following content has been provided by RWTH Aachen University.
Welcome everybody to today's current topics in HCI class. We will continue from where we left off 2 weeks ago, since there was no class last week. You might remember that we talked about ethnographic design, ethnographic HCI research and engineering and design research. And we went into more depth than into the experimental research in particular, because that's the one that our branch of HCI, if you want, the one that, with your background, you're most likely to encounter and do yourself. That's the one that we're going to be looking at in more detail. We took a look at protocols. We didn't want to confuse you there, but protocols are basically an internal aid for you that you might write for yourself just in order to plan and structure your actual study. Right? It's usually not something that you publish completely, but it will contain a lot of things that you can go back to. It's kind of like a lab notebook, if you want, that you can then go back to, and you pull things out of that and put it into your publication, your paper, or your thesis, whatever you might be writing. A lot of people, by the way, that end up doing their master's thesis here at our lab often also end up contributing to a paper. That's the way that we try to make things work for many projects. This is sort of our intended and announced goal, that if the work turns out great, then we can actually use that as part of a publication that we are working on in this field. So oftentimes you will find that, as a master's student, students often write things basically for their thesis, but they also can reuse parts of these things in informing their paper writing. All right, so we're going to continue and wrap up the discussion of experimental research today. And then we're going to take a look at how these things get published and how they get written up. And we're going to take a look at a paper as an example to really talk you through what are the key components of a good CHI paper. But first of all, a few more words about experimental research. One thing that comes up a lot, of course, are the variables that you are dealing with in your research. And we already know that there are independent variables and dependent variables. Independent ones are the ones that you actually twiddle, that you control, and the dependent ones are the ones that you measure. And in the sort of highest level, if you want, or the most, the kind of experimental research that gives the most concrete results, we tend to look for causal relationships between the independent variables that you're changing and the dependent ones that you're observing. So what kind of independent variables do we have? This is something that you might remember from statistics. There's like a gray, hazy mist in the back of your mind from your first semesters taking a statistics class. We're going to go back to this, and you might find that now a lot of these concepts become clearer because we actually need them to model the kind of research we do. So these different kinds of variables that we can see are ordered in the way that I present them. Basically, the further down the list we get, the better for you. What I mean by this is the further down we get in this list, the more statistical methods you can apply to your data. You can't apply the same analysis method to every kind of data that you're measuring, and we're going to see why in just a second. So the sort of least satisfying, if you want, scale that you might get variables on is called the nominal scale. To give you an example, you might have two input techniques, right? You're trying to compare how fast is mouse input versus touchscreen input because you just invented, the mouse or the touchscreen. So that would be your independent variable. And mouse and touchscreen, you can't order these, right? The mouse isn't more or less than the touchscreen. There's no sense of ordering these two different values, if you want, for your variable input technique. So your independent variable would be the kind of input technique that the user is using, And the values for this, or treatments, sometimes we say in statistics, for this variable input technique would be mouse and touchscreen. And since they have no ordering relation to, and you can't measure, like, how much is the difference between mouse and touchscreen, that's not a useful sentence. So this is a typical nominal scale variable. They're fine, and sometimes that's all you get. There's just not more in the variable, in the nature of the variable, than this nominal scale. But it will mean that you will be limited in the kinds of statistical measurements you can apply to it in methods. On the side of dependent variables, this is also possible. For example, you might have an experiment in which, or somebody might report an experiment in which they just check whether the user makes a mistake or not. And again, there is no more or less here. We're not measuring how many mistakes they make, how many errors they make, or anything like this. We are just saying, did they make a mistake or not? That's a possible design, but it will limit, again, the power of your statistical statement that you can make. The statistical deductions you can make will be limited because this is just a nominal scale variable. So what you're already beginning to see here is independent variables, often you kind of have to live with what you get, right? That's the thing you're measuring. You can't really tweak that. But with dependent variables, we might be able to actually come up with cleverer variables that we observe. And by doing that, we might move down this list of scales and get to a richer statistical analysis, a more powerful statistical analysis that we can apply. So for example, if we had said that we're not just going to measure whether the user makes an error or not, but we're going to measure the number of errors they make, then we're already moving down in this list to more powerful scales and to more powerful statistical methods. The next one is the ordinal scale. An ordinal scale is a strange beast. It gets very easily confused with the ones that come below it. The reason for that is that now we have an ordering of the different values of our variable, or the different treatments that we apply to the variable. But the ordering does not suggest a measurable distance between each. So if I was going to test blue and red buttons and see which ones work better, cannot be ordered, right, in any useful way. It's just like mouse versus touchscreen. But if I say I have small, medium, and large buttons in my study, then I have an ordinal scale. I can say medium comes between small and large. That clearly makes sense, right, from a variable point of view, from a value point of view. But I am not saying how much the difference is. So I'm not measuring key size in square millimeters or anything like that. So there are some cases in which you have these ordered categories that do not give you a measurable distance. A very common one is on the side of dependent variables. And this is from, and you might remember this from DIS1, the famous Likert scale. Likert scales are scales that you often use in questionnaires when you are trying to get an answer out of the person answering the questionnaire that you want to subject to some kind of statistical analysis. So you're not just giving him an open text field, what did you think about the interaction, but you're, for example, asking them, you give him a statement oftentimes, something like, I had no problems using the prototype. And then you give them a 5-point scale, which is often something like, I fully agree, or I mostly agree, or I'm in between, or I mostly disagree, or I completely disagree. This would be a 5-point Likert scale. So clearly, from I fully agree to I fully disagree, we have a change, right? We have an order of these answers. It's clear that one kind of answer comes between, answer value comes between two others, for example. But we cannot say that there is, a difference of one between fully agree and mostly agree, or mostly agree and I'm on the fence, there is no useful measurement, no distance that we can measure. So this is a very typical ordinal scale that you see in dependent variables a lot when people do interviews and questionnaires. And it's often confused. They think, oh, I got a value back from 5-point Likert scale. That's basically 1 to 5, or if you're a computer scientist, it's 0 to 4. And then you're going to start doing measurements and saying like, oh, we're in between 2.5 and 3, and that's the same kind of distance as between 1.5 and 2. But that's not right. Those kinds of measurements are not legal, because the user who answered this was not imagining a numerical score in between these, or any kind of like continuous distribution. It's just ordered values, but there's no clear distance measurement. Next up, down in our list, but up in sort of the usefulness, is an interval scale. These are also kind of strange, but a best example for that would be temperature. So what I mean by this is, with temperature, you have a sequential order of degrees, right? You could say we have 1 degree, 2 degrees, 3 degrees, etc. But what is missing is a zero value, a value around 0. What I mean by this is, let's say you use the degrees Celsius. So you can clearly say, I've got a 20-degree measurement and I have a 10-degree measurement, and the difference between these two is clearly 10 degrees. So the interval is measurable, so you can determine relative distances, right? And you can say that's the same distance, the same difference as between, I don't know, 450 degrees and 460 degrees, or between minus 20 degrees and minus 30 degrees. What doesn't exist in this case is a zero value that represents the absence of any kind of measurement. Now, of course, there's a value of 0 degrees. Sure, in Celsius, that's when water freezes. But that is just a random point in this temperature range that was chosen at some point. So you cannot say 20 degrees is twice as much as 10 degrees. That doesn't make sense. The moment you'd convert that to Fahrenheit or Kelvin, you see that this claim no longer stands. So temperature is a good example of an interval scale. It's sequentially organized. All the categories have the same size. In this case, you could say like 1 degree increments, for example. So you can determine relative distances, but a ratio between two values doesn't make sense, right? And that takes us finally to the, if you want, most useful kind of variable, and that is called a ratio scale. A ratio scale is an interval scale, but it does have a value of 0 that represents complete absence. So that means that you then can determine absolute distances, not just relative distances, and thus you can also compute ratios, right? So best example, and these are actually fairly common. This is usually the one you try to go for in your dependent variables for sure, if you can make it work, because it's the one that lets you use the most powerful statistical analysis tools. A typical example would be task completion time, right? So you give people something to do, and everybody will need a different amount of time, but it's clear that there is a 0 point, right? If somebody magically needed no time at all, that is clearly the 0 value against which you can compare. And it makes total sense to say this person took 15 seconds and this other person took 30 seconds. So the second person took twice as long as the first one, right? All these things start making sense. Usually with these kinds of things, you also don't have a negative range, right? So a 0 really means there is an absence of the value, if you want, right? An absence of task time, for example, in this case. Or the error rate, good example, right? If the error rate is 0, then that means there's an absence of errors. No errors were made, and we can immediately start using ratios between different people's results and claim we had an improvement by 25% or something like this. This doesn't make sense in the interval scale or any of the others up there. So claims like, oh, we measured on a Likert scale, people gave us a on 1 to 5, they gave us a 3 in one case, or a 2 in one case, and a 4 in this other condition. So it's twice as good. Doesn't make sense, right? Because you use the Likert scale, so you cannot use ratio computations. And then, of course, you can also have a ratio scale on the independent variable side. Let's say the amount of time that you turn on a light, right? In the classic experiment where you want to prove Bloch's law or something like this, right? You could say how long was the light on for, and then you could use that as there's a clear 0 value there as well. All right, so this is important to understand. Whenever you choose a statistical method, you got to make sure that the kind of variable, the nature of your variables, the scale of them actually applies to your method that you're trying to use. This goes back to DIS1 as well, so I'm just going to go over this quickly. There are 2 basic experimental designs that you can choose. One is the between groups design, which means I have the blue box here represents an independent variable, and it can have the value A, let's say keyboard, or B, let's say mouse for input, right? And I manipulate that, so that's the one that I change. And some people get the experiment with the value A, some people get it with the value B. That's the between groups design. The other version is the within groups design. So here I have a user, and I first let him use the system using the keyboard, value A of my variable input device, and then I let him use it with the mouse, variable value B of my variable of my independent variable input device. That's a within groups design. Now you might recall from DS1 that these both have their their pros and cons. Clearly, with the between groups design, what you're facing is if everybody is only doing one variant of the experiment, that means that your group falls into 2 at least. Right? If you only have 2 treatments or 2 possible values of your variable, you only need 2 groups. Great. If you have 3 different values, 3 different input devices, let's say, or 3 different button sizes, you need 3 groups, right? So this gets out of hand quickly. And what we typically, in a 2-value setting, we typically say we have a control group, which is the one where we use the default setting, and then the treatment group is the one where we try out our new strange thing. This is often in medicine. You have the control group gets a placebo sugar pill, and the treatment group gets the latest anti-corona drug or something. Now the advantage of this is, of course, if we split it up that way, there is no practice effect, right? There are no effects of people carrying over any kind of effect from one condition to the next, because they only get exposed to one condition. The disadvantage, of course, is you need many more people, right? You need a lot more people, because with 2 treatments, you need twice as many users now than you would have needed with a within groups design. If you have 3 different values for your variables, you need 3 times as many people. Still, this is a good choice, especially if you are doing something that has very simple processes with limited limited cognitive processes. So what we mean here is things where most people will probably perform about at the same level, right? So for these, this is actually fine. So if you want to test reaction time, you can probably split any user group just in half randomly, and as long as you don't put all the old people in one and all the young people in the other, as long as you keep that sort of balance, and you don't have any obvious differences between your 2 groups, you're probably going to see the same results, because reaction times are not that drastically different between individuals. So that's why we say limited cognitive processes. Basically lower level cognitive processes in our brain are things that you can easily split a group, and then you avoid all the learning effect shenanigans, and you basically still get reliable results. Within groups design means everybody does all the variants of the experiment. Now you need fewer users. You only need, your normal standard number of users that you want to use for your experiment. And you have another nice effect, which is that if there are individual differences between your individual users, you've got some, really slow, some really fast learners, for example, they will all get exposed to all of your conditions. So those differences will tend to cancel themselves out, right? Because the faster learners will be faster with both of your systems, and the slower ones will be slower with both of your systems. So it's not going to impede on your statistical results measuring differences between your two systems. The disadvantage, of course, is that you can get practice effects. And we're going to talk about what these could be. But we tend to say that if you have complex tasks, typing, reading, especially reading comprehension, right, where you ask people to read and then repeat or decide something, composition, any kind of creative problem solving or composing texts or documents or graphics, anything that basically requires, higher order functions, something that you couldn't easily, train a monkey to do, basically. There we also observe among humans the biggest differences between people, and that's why it's a good idea to then use a within groups design. A classic example is the systems that we've built that try to help develop programmers code more quickly, to navigate their source code more efficiently. And we gave them a programming task. Now, programming productivity is vastly different between people, right? There's factors of 20 and more reported in the literature of how fast coders can be. So, a thing that one person might take 10 minutes for, the next one might take, 200 minutes. So for that, we use typically within groups designs, and then we basically just expose people to the one tool, and then with a different task of similar complexity, we expose them to the other tool. And we might swap the tasks around between the conditions, but we're not going to expose one user only to one condition or only the other one, because the individual differences would be too dangerous as an external confounding factor. Now, as I said, within groups designs has that problem of learning effects or practice effects or order effects, which means that we may get behavior by somebody. Let's say we do our keyboard versus mouse study, typing or selecting things with the keyboard or with the mouse, and we measure that one after the other. And the user will probably, by the time they've seen the targets that we make them select for the first condition, they're going to be faster doing that in the second condition because they've simply already seen the task. So this is a typical effect, and it can play both ways, right? You can have carryover effects that are negative. For example, you might get something where the first condition, where the user has to do a lot of typing or something very quickly, and their fingers hurt. So they're going to be slower in the second condition. Or they can have a learning effect that goes in the other direction, where you basically say, well, we have simply because people were exposed to one condition, they will have learned something about the experiment as a whole that will make them faster in the second condition, no matter which one comes first, right? But the second one will always be faster than the first, relatively speaking, because if the user has learned something by doing the first condition. So this could be typically a practice effect, right? I try to make people play a game and they play it with two different controllers. By the time they get to the second controller, they're going to have learned the game a bit, and they're going to be a little faster just because of the practice. So what that means is that you get different results depending on whether people used, for example, your input controller design first or your special input designer control second in the order. The opposite could be true as well. Like the fatigue effect could set in, right? People just get tired of doing it, so they get slower as the experiment progresses. It just takes too long overall. Those are things that can happen in within groups studies. Of course, you can also see fatigue effects within if you have a between group study, even in one condition. If the experiment takes really long in just one condition, people might tire and get slower and slower over time. But that's usually something that you would then observe across all the conditions, and you could then maybe see that effect in your data and address it in your discussion. So within groups has this problem, and we know what to do, right? We can negate order effects to a degree, and that's called counterbalancing. We're using this logo here for anything that is the within groups design. And counterbalancing means we basically try to remove the effects that the order of conditions has. Now, ideally, you guys are computer scientists, so you can figure this out. What you would technically have to do is you would have to use all possible orders of treatments with an equal number of individual participants. So what I mean by this is we have a within group study. We have, I don't know, 2 different conditions. So with 2 different conditions, half of them would have to do condition A first, and then B, and then the other half does B first and then A. Sure. With 3 conditions, it gets a little less obvious, because now we need to have people do A first, then B, then C, and then we have to do A and C and B, and then we have to do B and C and A, and so on and so on. So all the different permutations of these 3 conditions would have to be used. Is there any math whiz kid in the audience here who could tell me how many different subgroups we would have if we did all the possible permutations on our let's say n different conditions? You can raise your little blue alien hand if you want. Come on, that's high school mathematics. In our example here, we have 6 conditions. So we need to basically, if we were to have every possible order of treatments in there, we're looking at basically all the permutations of 6 different conditions. Blue hand, come on, come on. That's not hard. You can say something wrong too, that's fine as well. Or you can not raise your hand, and that gives me the joy of just randomly picking somebody. Sören, what about you? I'm sure you have an idea.
Yeah, I think it's the faculty of
exactly. It's the faculty. So you're looking at basically 6 positions for the first condition, and then there's times 5 positions for the second one, times 4, and so on. So that's a lot of experimental subgroups, right, that you'd have to do. And remember, when you do this, you're doing this to remove the effect, but you still really want enough people in each of these subgroups to not get completely useless statistical results, right? Because now, strictly speaking, your experiment of one order is a different one than the experiment that you do with the other order. And you need a bit of meat on this, statistically speaking, so that you can show that your ordering effects were removed without breaking it down into just one person each, for example. So what people do, of course, is a compromise, and that's called Latin square. And again, we talked about this in DIS1, so I'm just going to go over this very briefly. What Latin square does is that it ensures that each condition, and mark this is important, each condition will appear once at each cardinal position, meaning the conditions A to F here will appear once at each of the these different rows or columns. And what we then also guarantee with the Latin square is that each condition at least precedes each other condition once, and it follows each other condition once. That's what the Latin square does. So the way you can do this is, if you look at this this column here, you can see that we have in the first column we've got A, B, C, D, E, F. And then we basically push them through to the top, right? See, the second column here starts with a B and has everything else pushed up one. the A rotates to the bottom, but it doesn't continue that way. It has an interesting pattern. I'm not going to go into the mathematics, how that works precisely, but there's a mathematical algorithm. It's fairly straightforward on how to construct a Latin square given a number of treatments. So for this Latin square, what you get as an effect is basically with 5 different or with 6 different conditions, for example, as we have in this example here, we only get 6 different orders, right? And if we do all these 6 different orderings, then what we actually end up with is that each of the 6 letters will follow and precede each other letter exactly once in these sequences. That's a compromise, right? It gives you some balance, canceling out of order effects. It's not as perfect, mathematically speaking, as the n faculty fully permutated orders, but much more realistic. All right, the other thing is a learning curve. Now, a learning curve can happen no matter whether you're doing within groups or between groups. It doesn't really depend on that. That's why we got both logos there in the corner. So a learning curve is an effect that means that people get better at doing something over time. And they invariably do, right? People are, the human brain is really good at learning. So if you put a user down and tell them to click on targets that appear in front of them, no matter what device you give them, after a while, they're going to get faster, but they get used to the device. So here in this plot, we see time on the x-axis and the performance on the y-axis. And you can see 2 different keyboards being tested here. The blue one is keyboard A. It starts with a pretty good performance at the very beginning in the first trial. And as the trials go on, it kind of gets better. There's a learning effect, a learning curve. But it kind of, you wait basically, after a while you see a plateau, right? So it seems that people have sort of maxed out what they can learn about using this. Keyboard B starts slower in the beginning, but actually after a couple trials, we don't know how long that is into the experiment. We didn't give numbers here, but at some point people actually get faster with this than with the first keyboard. So that's an interesting result, right? And you're quickly going to see that now you have to really decide, what is it that I want to really say about my research results? Am I interested in immediate usability? So in the usability at the very beginning that somebody encounters a system, then I should probably look at the values on the left-hand side. And then I don't need to run, then the long trials that go down the timeline are actually going to be not much use to me. Or am I interested in more of a skilled use examination? And do I want to understand how fast people will be once they've had a little bit of time to familiarize themselves with the system? And then you would be using the values on the right, in which case keyboard B seems to be the better idea than keyboard A, right? Whereas if you encounter it for the very first time, keyboard A seems to be the better choice. Now, in most cases in practice, what people do is they are looking for usability after a bit of familiarization with the technique, but not after 6 months, because most people don't have the time to wait that long and are not interested in those changes. And typically also, the learning curve flattens out fairly quickly. So what you will often find in experimental descriptions is that the experimenter says, before using each technique, users were given, 10 minutes to familiarize themselves with it, to do some practice runs, for example, before starting the actual measurement. So you get rid of the initial steep learning curve gradient, and you get into the area where it's more saturated. In the end, that's a design choice, how you design your experiment. And you're well advised to look at your data and look for this learning curve and try to figure out, I made it beyond that gradient, or am I still in the steep of that gradient? And if people had continued longer, there might have been actually a change in which technique is faster, like we see here. So if you end up testing people after an initial trial time that is before the orange blue line here across, then you would be getting one result. If you let them go until after these lines cross here, and you get most of your trials in this area after the lines have crossed, then you will get a different result. So the learning curve tells you, how experience or time, if you want, relates to performance. And we typically see a more rapid rise at the raise at the beginning, and then it follows by a plateau. So you try to measure usually when the learning effect is gone, because usually it doesn't take very long for it to disappear. And that's the more useful measurement, right? The moment I pick up a device for the very first time is not going to be representative for my, using it every day. Okay, so it's time to turn on your brains. We're going to do a quick in-class exercise, very simple one. Let's assume you have designed a new keyboard layout. So you've come up with a new keyboard input technique, and you want to know how good is it. You're going to test that as your strategy by comparing it to existing techniques. Right? So you've got your standard QWERTY keyboard, and you have your own new keyboard layout. And you want to find out which one works better. The question now is, are you going to test this in between groups or within groups, right? So, and what I would like you to look for is, what would be a reason to run this experiment as a within groups design? And what would be at least one reason to run this as a between groups design? So,
should we launch the poll first?
We can launch a poll. So
yeah.
What we can say is, if you think about both options and you've come up with what you think is the stronger reason for which design you would pick here, then you can pick the one that Anke puts out as a poll. So there are arguments pro and against both of these, but I'd like you to, in the end, you need to make up your mind as an experimenter, and you need to sort of pick something. Okay, so we had most people voting for within groups, but a couple of people voting for between groups. So I would like to hear it from both ends here. Can somebody give me a reason why you would pick between groups? Some of you guys voted for it, so you must have had a reason. What would speak for it? Okay, so what about within groups? That's more people who argued for that. Let's hear an argument for that. Leah, you look like you want to argue for.
Yes, I would say that most people have experience with usual keyboards, so the learning effect won't be that much, because they already know how to type on the usual keyboard. Also, they probably have different typing speeds and stuff, and therefore it's better to compare one person with both keyboard types.
Mm-hmm. So your second argument, definitely, right? People are going to be having quite radically different typing speeds. So in order to not make that affect our study, it makes sense if each person tries out both keyboards. The first part, though, if we say people have a lot of experience with the standard keyboard, I agree, but that is an interesting challenge, right? So that is really more speaking for, we should probably let people play with the new keyboard layout for a while to get some sense of how fast people can be. Oftentimes what we see is people introduce a new interaction technique in their papers and they measure it against established techniques, and people are faster with the established techniques simply because they've done them for 5 years, right? Like, I don't know, pinching on a smartphone to zoom in and out. That's been used so much that everybody knows it, and if you introduce something else, it's going to be harder for people to do that because they just haven't had as much chance to practice it. But you're right with the argument for the within groups. So what usually is tends to be preferred here is within groups design because you minimize the confounding effects.
We had just one more comment on the chat from Daniel.
Yeah,
which is learning design makes harder to unlearn and adapt.
Absolutely. Yeah, that's right. Once you've this is the big problem of the Dvorak keyboard, right? The sad story of the Dvorak keyboard being that it's the keyboard layout that would actually be faster to type on than what we all have in front of us, the QWERTY or Quartz layout. But since everybody's so used to the QWERTY layout, it's the Dvorak keyboard never took off, except for a small hardy base of fanatic users who use Dvorak keyboards. And show that it actually can be faster. We might still sometimes need a between groups design. For example, if you want to test whether a keyword favors users with right-handedness over those with left-handedness, or when you've got other kinds of interferences between conditions. So all those things that we talked about, the learning effects, the fatigue effects, can have impact, of course, on this. Okay, so. We're moving immediately into the second little experiment, which is going to kind of review your understanding of where you think all these things need to be placed. So for this, I would suggest take a few minutes to look at this. What we have here is a simple layout of the that you've already seen of an experiment, and we can see where scales play a role, where validity plays a role, what kind of things we manipulate, the independent variable up there in condition A and B, that we measure the dependent ones, the gray ones, and then we compare the two against each other. We have things that we want to control by holding them constant or by matching them or randomly assigning them. And we have extraneous variables, which ideally do not impact our data at all, but some of them can also become confounding variables and actually impact our measurements. And to the right here, we've placed a few keywords: learning curve, counterbalancing, Latin square, and order effects. So I'd like to understand where you would place each of these. Let's start with learning curve. Where would you place the learning curve as in this graphic? We've understood that the learning curve is a sort of is something we can observe, something that exists. And where do you think in this graphic it would belong? How about
we have also one answer in the chat.
Ah, there's something. Okay, all right.
Yeah, Mubashi says between A and B.
Ah, yeah, that just appeared. Thank you. So yes, that is right. The learning curve, but it's not necessarily. If it happens, it can confound your results, right? So what we saw in the graphic earlier is that the learning curve is something that happens with your experiment over time, with your user as he gets used to the technique. And if you don't know about it and you don't address it by giving people appropriate time to practice, for example, with each technique, then it may impact your results. So yes, it is basically in the comparison between the two, each of them basically, as you measure them over time, will get better, but they might get better at different ratios, right? The learning curves might be differently steep for both of your different conditions. So it can be a confounding variable, although you could also consider it basically just a factor of measurement that is happening over time. Okay, next up, counterbalancing. Where does that go? Okay, I'm gonna get out my magical.
Miguel put up a cent.
Ah, okay. Oh, I need to scroll to the top to see that. There you go. Yeah, Miguel, go ahead. Thanks.
I would put that next to manipulate, maybe. As we, because like counterbalancing is a method how we manipulate the variables. So I would put that next to manipulate.
Ah, okay. Okay.
Yeah. But I also saw in the chat that somebody wrote next to controls.
Mm-hmm. Yeah, but both of these make sense, right? So I think what we're doing is we are applying it to the way we manipulate the variable. But the reason why we do it that way is that we want to control something, right? Actually, the counterbalancing is usually there so that you remove the effect of something that you don't want to see, right? So it really belongs mostly into the whole space of controlling things by removing this effect that we otherwise would get if we didn't do counterbalancing. Next up, Latin square. Yeah, Sören, go ahead.
Yeah, right beneath counterbalancing, also in the control part.
Yeah, yeah. Latin square is clearly a method to control things, so a method of counterbalancing. In fact, I sort of stole one away from you guys. Random assignment is another way to do to try to remove order effects, right? If I have an order effect that I want to get rid of, and I do not have the possibility to do a full, all orders are going to happen, and I can't do a Latin square for some reason. Another way to do this is just to randomly assign sequences, right? To randomly pick from the order bag, if you want, and thereby remove the likelihood. In the case of two different treatments, that's basically the exact same as doing a standard counterbalancing, right? So if you randomly pick, then 50% are going to go first with one, and 50% are going to go first with the other condition, on average. Okay, so then we last one, order effects. This is something I'm going to show that here. You could consider it order effects also to be something that we try to control, but order effects, if they do happen as a problem, would really be something that sort of impedes your validity, right? So it actually has an effect on how you how valid your results are if order effects are still in your data. And the controlling mechanisms that we saw down there are trying to get rid of these. All right, let's take a 3-minute bio break, everybody. Get some air into your rooms, stretch, get up, get some drinks, and we're gonna see each other again in 3 minutes. All right, welcome back. So after this, we're gonna jump into how actually, how HCI research is published and how those papers are written and how these written papers are being reviewed. You've already learned about some of this when we had you look at contribution and benefit statements, but we're gonna take a very close look at a paper, and I'm gonna talk you through how this paper is structured and where each of the parts that make up a good paper are hiding in the text. This should help you in 2 ways, right? First of all, you should be able to read papers more effectively once you understand how to look for the parts and where they might be. And secondly, it should also, of course, help you write your own papers so that everybody else understands what you're doing. In the end, writing good papers, writing good text is like designing a good user interface for your ideas, right? For others to understand them. I always think of text writing as user interface design for the reader, right, of what you're trying to communicate. So with this sort of in mind, what are criteria for a good paper according to, in the field of HCI in particular, although most of these things are applicable in a much broader range. Remember that the key idea of academic research is to advance the knowledge of the community, of the academic community, right? So in the end, what a reader would ask themselves is, after I've read the paper, what do I know now that I didn't know before? And with knowing, I don't mean what kind of idea of a cool hack do I now have that I didn't have before, because for that I could just read, Hackaday or something. But the idea is knowing as confirmed scientific truth. So is there a new insight into the world that I now have that I didn't have before and that I can trust because it has been explained and shown to me in terms that I find well validated. So the key point of a good paper in HCI, but really in research in general, is of course its contribution. What is this new insight that this paper brings to the field? Right? That is the key criterion after which papers are evaluated. Does it actually tell us something that will be a major game changer that will really bring the field forward in some way? Do we understand something more about how people behave in HCI, or how a certain technology affects them, or how they work together using a certain technique, or which technique works best under the circumstances of jogging in the woods, whatever it might be? The contribution is the key. And you've already learned from contribution and benefit statements that we try to not just take a contribution per se, but also to understand what can we do with this. So while the contribution itself means I'm telling you something new, and this is a piece of knowledge that you can trust, and that is significantly new and unknown before. But immediately, at least in the HCI research community, the question is asked, well, does it also actually demonstrate something useful for the community? Is it something that researchers, or also practitioners, of course, can actually do something with? You will often see that contribution and benefit statements try to address benefits in the sense of, does this help other researchers in the field? For example, by presenting a new theory, or does it help practitioners by showing to them that this new design of a keyboard is actually faster than anything else that's out there on the market today? So these benefits might be practitioners or researchers' benefits, but those are the two key things. Then somebody might be presenting something that is fundamentally important and a huge benefit to the community, but everybody already knows about it. So it's not new, right? So novelty is something that needs to be tested. And this is super tricky because we don't have an algorithm that we can just run and say, okay, nobody's ever done that before. We can only give whatever the author presents to others from the field who've worked in the field and ask them, have you seen this before? And naturally, their coverage of the existing literature will be spotty, right? It's never complete, given that academic publications are developing at an exponential rate and have been doing this for decades. The knowledge doubles more and more quickly, so nobody can really keep up with everything happening in their field. So in a way, the person who knows best about the field is usually, hopefully the author themselves. So the way that we expect authors to argue for the fact that their thing is new is we ask them to tell us about everybody else they know about, every other project they know about that comes close, right? So we want to understand, is the thing that you present really something nobody else has ever presented in this way before? And you can convince me of that by showing me how close everybody else has gotten to that. So we are interested typically in what we like to call the closest competitor to somebody's work, especially if you're in the area of HCI research where people publish artifacts. So for example, a new interaction technique, you want to know about all the other interaction technique options that people have presented before and how they would then, why yours is still better, how they would compare to it. So you usually find out about the novelty of something by reading the author's related work section, and then hopefully, if the paper has gone through a proper review process, the section not only reflects what the author thinks is the related work, but also, since people have read this paper, reviewed it, and given their feedback on it, and only accepted it for publication after the feedback was addressed, usually this section should also include the knowledge of the greater community, right? Because a bunch of reviewers have looked at it and have also said, hey, you've missed this paper and you should set it apart from this research. But still your work is unique and new and novel, so it stands as a publication. Or more often than not, somebody writes an awesome paper and a reviewer says, this is great, but I've read the exact same thing or very close to the exact same thing 3 years ago in this other paper that you're not mentioning that you maybe weren't even aware of. And usually then that paper doesn't get published because it's not novel. We also have validity, right? Are the claims that the author makes properly backed up? I could claim I have invented a new input technique based on rubbing your nose against your smartphone that is faster than any text input technique that you could imagine. Well, you probably want some proof, right? So, and that's what you will find in the validity, where I show you that my technique that I developed is actually faster than everybody else's. But I'm looking at a lot of this from this artifact-based HCI research simply because that's what we do so much. But remember when we looked at all the other variants of HCI research, you know, the GPS study in cars, for example, that there can be other ways to validate your research. It's just important that you have some kind of validation. A validation isn't always a user study. And then oftentimes you wonder, does this paper match the likely audience well? So is it something that, you know, this is closely related to contribution and benefits, of course, but you want to understand, does somebody submit a paper, for example, to a technical user interface conference that is very much about design questions or about a theory or about you know, an expansive study that doesn't contribute a new technology? And you might say, well, you know, you shouldn't have submitted this to WIST. You should probably send it to, you know, DIS or CHI or something like this. So you might find that sometimes papers get rejected and the authors get told, this is really great, but it's a different scope and you are better off submitting it to this other conference. And then finally, they should be self-evident. You want what the author is trying to communicate to be presented as clearly as possible and with great care given to the written presentation, the diagrams in there, the figures and graphs, any other visuals, but mostly, especially the text. So the text should be easy to read. It should be proofread carefully before submitting. It should be consistent, and if it introduces a new term, it should use that term consistently throughout the paper. And it should be written clearly so that the reader is really taken by the hand, if you like, and guided through the author's thought process. And it is amazing how hard this can be, because you are a researcher, you've come up with something awesome, you know everything about it, and now you're supposed to write it down for somebody who knows much less about it. And this gap between you, the all-knowing author, and the reader who needs to, you know, understand this topic fresh from reading your paper is big. And a lot of authors do not manage that gap, bridging that gap, which leads to papers that you read and you're like, this all seems to be really cool, but I don't understand what they're really doing here, or I don't understand why they're doing it, or how they're doing it, or what the end result is, or whether the prototype they built is their key contribution, or the study, or what is going on. And it's mostly because authors forget to mention that. So just a quick recap on some of these points. So we've already talked about contributions, benefits here at length. Validity falls into two parts. You have internal validity, which basically means in a study that you run, in an evaluation that you run in your paper or in your research that you publish, you try to have a single unambiguous explanation for the relation between two variables, right? So what I mean by this is you run a study and let's say you are measuring, I don't know, typing speed, because we're so creative today. So you're measuring typing speed, and you have two different devices and you decide to go for within groups design. We've already said we want to do that. And just to avoid further bias, you pick all the participants from, let's say, you know, the same, you know, basically your fellow students, right? Now, that gives you a very homogeneous group, and your results are going to be pretty clear cut because you are basically studying it with 15, 20, 30 people of basically the same demographic, right? 30 computer science undergraduate students. This is going to give you internally highly valid results, meaning that your results are probably going to have nice, differences and clear differences in performance and narrow, standard deviations and so on. But it will also mean that externally, it may be not so relevant because it's hard to generalize the results you found from undergraduate computer science students' performance to generalize that to the population at large. So a lot of things can threaten internal validity. What I just described is one threat, that you don't have a well-balanced user group. That would be a typical confounding variable. Another threat is experimenter bias. That's the one when you do your master's thesis like Anke did. She builds this tangible-based system, and then she lets people try it out. But when she explains the study to them, she might say, well, try out the system and try out this other standard way of doing it, and then try out my awesome system that I built for these last 6 months and that I hinged my whole life on. And then, of course, people are influenced by this through the experimenter's bias. Learning effects are another thing that can threaten your internal validity. We already talked about those. Or the so-called Hawthorne effect, which is that just by observing, you might change behavior. It sounds a little weird, but it actually happens quite frequently. For example, if you want to observe how people go through their mail and you start looking over their shoulder, they're going to be more self-conscious about what they do. They might actually not follow that random link in that spam email that they got that sounds like an interesting link to a YouTube video, because they think like, that's not the proper thing to do. So being observed can cause changes that would also threaten internal validity. Okay, so that's internal validity, making sure that what you measure, you find a clear explanation and an unambiguous explanation for the relationship between two variables that are changing. The external validity is how far can we generalize the results to other people or to other settings. You might run, for example, a lab study is a key example. Lab studies typically have fairly high internal validity because you control everything. Everybody is in this white room with just one table and so on, but it is not their natural work setting. So if you're testing a group calendar scheduling app and you test it in this lab setting, it may not be as realistic as them actually being in their office, where they've got a clock on the wall and a paper calendar on the wall and so on. Or other times of the day when the system gets used, other than that, what you did in the lab, or other ways in which performance is measured. You might, for example, introduce a system to type text, and you measure characters per second, but actually what's much more important is that people type without mistakes in their job, right? Maybe they are copy editors that need to correct writing. So they are not that much caring about how fast it is, although it's also important, but they might be more worried about how accurately am I typing. So anyway, any characteristics that are different from what you did in your study could impact your results. So the threat is if you basically say, oh, we studied this with undergraduate students, and I'm sure it's going to be the same for everybody under the sun. Probably not, right? So your external validity goes down if you have a very homogeneous user group in your study, for example. The other thing that can threaten your external validity, if you have more than one independent variable and they might have interference. So you were not able to hold down everything except for one variable and just twiddle that one, but you had to twiddle two at the same time. And then you don't quite know, well, which of these two actually caused the change, right? So that starts then threatening your external validity. Unfortunately, external and internal are always a trade-off, right? So you have to strike an appropriate balance based on what your research goal is. If you want to prove something about very fundamental psychological processes, probably going to be a very controlled lab study with little meaning in the real world as it is, but it may help explain things that are more complex that are happening in the real world. If, on the other hand, you want to do something like what we saw in the UCSD study, how does introducing video narratives change the instructional, behavioral patterns in dental hygiene practices? That's not something you can study with people sitting in a lab, right? You need to go out and observe where it's happening. Originality is the last part here, basically just saying what is new and what are the new ideas, what are the new approaches. Overall, of course, the clear contribution to HCI is the key point. So now we're doing something that we haven't done before in this class. We're doing this for the first time this year, but I think it's very helpful to understand how HCI research gets published. We're going to take you through a walkthrough of a paper. This is the paper that you guys already know, force ray, extending thumb reach via force input stabilizers, and so on. Written by one of our former PhD students who finished up recently, Christian Kors. He was the lead researcher behind this. But Marcel, Simon, and I are still here. So, and this paper was published at CHI with good reviews, and we want to use this to show you where stuff is hiding. Let's start with the beginning. The heading, the title of a paper is actually, if it's done well, is actually very revealing of what you can expect from it. So, in this case, the heading here and the so-called figure 1 are telling us quite a few things. For example, we can clearly see in the heading what the contribution of this paper is. The contribution is that it is using force input in order to extend the reach of the thumb. That is the contribution. So using force, not something else, right, to extend thumb reach. That appears to be the contribution if I only read the title. And why is that interesting? Well, that's the benefit, right, in a way, because it stabilizes the device grip for mobile touch input. So we have contribution and benefit already laid out essentially in the title. Also, because the title starts with a proper name like force ray, this is a very strong indicator in the HCI research and also in other engineering research areas that we are dealing with an artifact contribution, because force ray is the thing that is introduced with this paper. So just by weird name, colon, and then comes something else, you can almost always say, aha, that's probably an artifact contribution in here that has gotten this proper name, that the project name essentially. Figure 1 is another thing that people often overlook, but a good paper pays very careful attention to designing a great starting figure for that paper. Figure 1 is the first graphic in the paper. It's usually on the first page or second page. And it's usually the first thing people look at after reading the title, even before reading the abstract, simply because your eye is drawn to the graphic. So if that graphic does a good job of laying out, again, what the key contribution is in this paper, remember, contribution, right? That's super important. It's like, with houses, the three things that determine the price of the house is location, location, and location. And the three things that determine the success of a paper is contribution, contribution, and contribution. So here in the figure 1, we can see, we highlighted this here, that the force ray interaction technique addresses this reachability issue without destabilizing device grip, right? So the graphic shows us, somebody is touching down with their finger, then they're moving it around, moving this weird ray, then they start pressing harder and harder, shown by these increasing arrows there. And as they press harder and harder, this little dot seems to move out to a target. The target highlights. user suddenly lets go in figure E, and then the selection has been done. So the graphic shows us what's going on. There's a little timeline below it showing us the force pressure over time. So by looking at that and by reading the caption for figure 1, which should also be written carefully, explaining to us what we see and why we see what we should be observing in this graphic, we've got contribution and benefit basically laid out. Next comes the abstract. And again, to the right here, I always have these things, right? Contribution, benefit, blah, 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 blah. The abstract is the next thing people typically read when they've read through the title, looked at figure 1. And here, you can also find that the contribution and benefit are laid out quite clearly, especially though it starts setting things apart from what exists. So the contribution is once more made up here, right? So the first couple sentences introduce very briefly the problem, motivating where we are. And force ray lets users aim at outreach, blah, 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 by applying force, etc. So that gives you the key contribution of it, explaining it a little more. And then comes, in the first study, this was that much slower and that much had higher selection rate than the best existing technique, but caused significantly less device movement than all other techniques. So it's already explaining we are not going to be the fastest or the most accurate, but we're going to keep people from dropping their phones. Basically, that's the key message here. So this is showing where the novelty of this thing sits. You could also say in a way that this is part of explaining the benefit of what we're doing. Now, after that comes the introduction, right? And I don't want you guys to read through all of this, but I want to show you where things sit here. The introduction typically gives you a very quick summary of what the problem is that we're looking at, motivating it, and thereby also saying what has already been done and why we're doing this new work, right? So here, this basically lays out this first part, what the problem is, and that various ways have been proposed, but we still have problems with significant device motion happening while selecting targets because of these techniques, especially in one-handed use, right? This is what this is about. And then comes the introduction of force ray. Again, we have more contribution statements here. We have a statement here on the benefit, benefits natural, I should be real, yeah, stable grip, etc. So it gives you the chance not to drop your phone. And we have more claims to the key contribution. See, in the introduction here, this paper actually is nice enough to say, thus, the key contribution of this paper is the force ray interaction technique. And then comes something interesting that you will often see in papers that they explain in the introduction what the rest of the paper looks like. It's kind of like a preview of what's coming, right? And the remainder of this paper, we do this and this and this, right? We first review related work before describing the design and implementation of force ray. And to validate it, we present 2 user studies, right? So a good paper will already give you the lay of the land right there. So you already know what to expect, right? It makes it really easy to read through the paper. You know now that you can expect 2 studies. So that's helpful to see. And closing with recommendations to address reachability issues for one-handed smartphone use. So what this paper also does is it doesn't just say, here's force ray, and we think it's cool, and here's the performance, but it actually goes one step further. It says, now that you know that force ray exists, and we've talked about the other techniques, we've compared it against them, we're going to give you some design guidelines as a practitioner if you want to apply a technique for this kind of selection problem, and we'll tell you when to use force ray and when to use something else. So you see, beyond the pure academic contribution of a new technique, we're also giving people sort of a cookbook recipe on how to apply the knowledge that they get here. This is, of course, very welcome in the HCI community because it really increases the benefit of this paper, especially for practitioners reading this. Then we get into a related work session here. where we have a whole bunch of different things laid out. Related work, obviously, is mostly going to be about novelty, right? So when you read through all of these things, then most of what you get here is going to be about setting this work apart from what already exists. And the way that a good paper does that is by not avoiding the confrontation with the competition, right? So clearly describing all the closest competitors and any other work that we need to know about so that we can really judge the originality of this contribution by ourselves as readers and as reviewers. But it also doesn't talk down the other research. Sometimes you get papers that say, well, these guys did this and these guys did that, but basically all is completely useless because we have the most awesome research here ever, and it puts everything else to shame. So it's always important when other research is being presented, when you write this in your own master thesis, right, that you say, what is it that I can learn from this other research? What is the key thing I'm taking away from this? You as the author, but then also the reader. And B, even with this other research in place and existing, what and why do I still need to do my own work? Why is my own research still relevant? Now, you might say somebody invented a really fast text entry technique, but it doesn't work underwater, and we are interested in text entry underwater. So we still need to do this, but we can get inspired by this other work and build on top of it. And if you read through this related work, you often see it structured by different subdomains, right? That basically give this long block of text a little bit of shape. And it will list a lot of references. This is where you find usually 90% of the references of a paper are going to be in related work, obviously, because they're pointing back to existing work and putting that into perspective. A good written related work section is worth reading the paper by itself, even if you're not interested in what the authors did themselves. If they wrote a great related work section, you're going to learn about the whole field because they do the review of that work for you. And then we basically see at the end of the related work, none of these solutions exploited force input. Benefits to self-reachability, learn for one-handed smartphone use. So this is basically where you see where we're wording, even though that related work exists, this is why we still need to do our work here in ForceRay. And then comes an introduction of the technique itself. That's a typical next thing to see for a paper like this, where you just basically get an explanation of, okay, this is how the technique works. Here, this will also include benefit statements, right? So this will also include explanations of why this technique is useful in more detail. Oftentimes you see a claim very short in the title, you see it expanded a little in the abstract, you see it again in the figure 1 title, figure 1 caption, and you will maybe see it again as the key contribution statement in the introduction, and then you will see it again when they explain their design technique, and probably again in the conclusion of the paper. So good papers really make sure that you understand what their point is. And then there is the study section, basically, right? So this is, the technique has been explained. So now we get basically to the part where we have the validation. And you guys have already looked at this part. So let's hear some ideas. What do you think we can see in this section here? What do we find in this section? It describes the study setup and of the first reachability technique study setup. Yeah, Christoph, go ahead.
I would say we get the validity of the claims because we know how the technique works, and now we have to prove it. And also in this particular example, I think it's also a bit of novelty because the force ray is compared to the others in the figure too.
Mm-hmm. Exactly. So most of it is going to be validity. Sure. I mean, that's what you would expect from your study. So it explains to you why and how the study shows the claim that the authors want to make. And the claim basically comes out of the study showing that force ray actually makes people move their phone around less while doing one-handed tapping tasks. But you're right, novelty is also in there, setting it apart from existing work again and showing that there is a clear jump ahead in certain areas. Not in everything, but in certain areas. And then we see some references here to areas that are more about the format, if you like, of the presentation. So these are things where you can see that the paper took great care to provide information in a clearly structured way, right? That's why we highlighted some of these things in the format space. And this continues on after the study has been presented. There is the results section. And again, you can see most of these things in the format, of course, giving you the contribution, right? So this is the key things that we find from our study. The key contribution here, therefore, is not just the technique itself, but also its performance and how it performs compared to others. Laid out again in a combination of textual descriptions and graphs that make the resulting data easy to read and that point out the key findings in visual form as well. It puts in several things that have to do with the benefits. So for example, the graph here on the very right-hand side shows how big the range of tapping targets was with different techniques. And you can visually, at a glance, see that the range where people need to tap is smaller for force ray than for the other techniques. Meaning that you don't need to regrip your device. This continues on with the discussion of things. So again, pointing to a nice structure here. The different techniques all got names. Force ray got an FR, and the other techniques got short names, so we could refer to them often and easily in the paper. We have more addressing of the benefit of what was happening here, but also going back to contributions. We now see here actually as the part of the after discussion, we see here the contribution of the additional guidelines that I mentioned initially that go beyond just presenting the technique and validating it. Well, and the last part in this paper is limitations and future work as a title, and then finally a summary and conclusion. Limitations and future work is an important thing. This requires the author to think critically about their own work and be open about anything that they think limits their findings. And a good paper contains that, not just claiming that everything is hunky-dory, but also being open about limitations of their own work that they can already see. It's much better if the author puts these out clearly than if reviewers or even readers find these later, right? We don't want that. So we want the author to be open and clear about what limitations the research has. For example, this cannot be applied to, I don't know, very large devices like tablets because we were only looking at one-handed phone input with devices of the following sizes, right? So it's a typical way to show that you're humble in your assumptions about how far your results can reach. And then finally, summary and conclusion is a good part to read early on when you skim a paper. We talked about how to read a paper, in the skimming technique. And the summary and conclusion usually reads similar to the abstract, but looks at things more from a post hoc perspective. And summarizing, once you've read all this, these are the key things you should take away from what we did. All right, we're out of time for today. So I hope that this gave you a good idea of how a paper is typically structured. We've talked about more details on how to do studies and evaluation and statistics. And we've seen how once you have your research lined up and conducted, how you actually put it into a format that other people can benefit from it by sharing it. Because that's how science works, right? We often get the complaint, a lot of people will say, well, you scientists, you don't work with other teams. Why don't you constantly collaborate with other teams from other universities? We do all the time. And the method of collaboration between academic institutions is publication, right? I write my paper, I write it so that everybody in the whole world can pick it up, read it, and build on those results. That's the #1 collaboration method that exists in academia, and that sets us apart from companies that would like to keep their findings for themselves because they want to keep the competitive advantage. All right, so this is it for today. Thanks everybody for listening, and we'll be back again next week. Bye-bye.
This content was provided by RWTH Aachen University.